Hello everyone, welcome to my presentation. My name is Rahmat Vijay Wijaksana Putra. I'm a PhD candidate from Technische Universität Vienna, Austria. I'm advised by Professor Dr. Muhammad Shafiq from New York University, Abu Dhabi. And in this opportunity, I would like to present our work with the title of Resilience and Energy Efficiency for Deep Learning and Spiking Neural Networks for Embedded Systems. Current trends show that the neural network competition model have achieved the state-of-the-art performance for a wide range of machine learning applications such as image classification, object detection, healthcare assistance, and even autonomous driving. And because of this potential, bringing the capability of neural networks to resource and energy-constrained embedded systems is an interesting research direction because it might enable a wide range of application at low cost. The competition model of deep learnings or deep neural networks or simply DNNs typically consists of multiple convolutional and fully connected layers. And here the synaptic weights are trained using the supervised backpropagation techniques. And to this day, many DNN models have been developed. And current trends show that the large DNN models can achieve higher accuracy than smaller ones, but it comes at the cost of larger memory footprint and energy consumptions. This fact makes it challenging to deploy them for embedded applications. Meanwhile, the computational model of spiking neural networks, or simply SNN, is more biologically plausible because it employs a spike-encoded information, spike-based computation, and also localized learning in each synapse. For example, by employing spike uh, timing-dependent plasticity or STDP learning rule. And because of these characteristics, SNN has the potential to achieve ultra low power and ultra low energy consumption while providing unsupervised learning capabilities. And to support this potential, state-of-the-art works consider a fully connected network architecture with a pair of excitatory and inhibitory layers. And current trends also indicate that large SNN models can achieve higher accuracy than the smaller ones. And again, it comes at the cost of larger memory footprint and energy consumption. So the challenging question is that how to perform neural network processing in an energy efficient and resilient manner for embedded applications. There are different resilience threats that can affect the neural network-based computing systems. They can come from hardware-induced faults that originate from approximation errors due to the employment of a reduced voltage memory operations and approximate compute units for power and energy optimization. And they can also originate from manufacturing defects due to the imperfection in the fabrication process. Furthermore, they can also come from high energy particle strikes that alter the behavior or values in circuits. And these faults can manifest in the form of bit flips, stacked faults, and erroneous output. Another source of threats comes from dynamic environments that require the system to constantly adapt to different tasks or new features that come from different environments. And this threat manifests in the form of obsolete information, which leads to low accuracy at runtime. And all these resilience threats might lead to system failure that might be crucial for safety critical applications. In the aspect of improving the energy efficiency of DNNs, one of the prominent approach is through DNN accelerators. However, most of them only present isolated accelerator design and do not truly study the impact of DRAM-based off-chip memory accesses. Therefore, considering that the DNN model is large and cannot be mapped on the accelerator fabric at once, then the redundant DRAM accesses are inevitable, and thereby dominating the overall system energy. Similar trend is also observed in the SNN, as the DRAM accesses still dominate the overall energy consumption of SNN accelerators. This observation exposed that DNN and SNN-based systems still face energy efficiency challenges due to the DRAM-based off-chip memory access energy that dominates the total system energy. Therefore, it is important to have techniques that can improve the energy efficiency of DNN and SNN at low cost. The aspect of resilience of SNNs against hardware-induced faults, recent work still focus on studying the fault modeling in SNNs and also the impact of random faults on accuracy. Therefore, the impact of hardware-induced faults on accuracy, considering SNN hardware architecture and the respective fault mitigation techniques, are still unexplored. Meanwhile, in the aspect of resilience of SNNs against dynamic environments, recent solutions employ different techniques such as larger number of neurons and synapses, additional neuron operations, complex exponential calculation, and also non-proportional quantities of the training samples. And however, these techniques still incur a large memory footprint and additional operations and thereby energy consumptions. Therefore, it is important to have a techniques that can improve the resilience of SNN at a low cost. To address this challenge, in this PhD work, we propose the following methodology. First, we investigate the techniques for energy efficient DNNs, and here we propose a cross-layer hardware and software optimizations. For instance, optimizing the DRAM accesses, employing effective data mapping on memories, and exploiting new DRAM architectures. Second, we investigate the techniques for energy efficient SNNs. Here we also propose a cross-layer hardware and software optimizations, for instance, by optimizing the SNN operations, improving the STDB-based learning, employing the quantization, and also approximate hardware. We also investigate techniques to improve the resilience of SNNs against hardware-induced faults, for example, approximation-induced errors, permanent faults, and also transient faults. Here, we propose hardware-software-based fault-aware training and mapping, weight bounding, neuron protection, and the respective hardware enhancements. And we also investigate techniques to improve the resilience of SNNs against dynamic environments because the knowledge of offline trained SNN might be obsolete at runtime. Therefore, we propose adaptive learning, memory energy estimation, as well as parameter enhancements. And in this manner, the output of this PhD work are the resilience and energy efficient deep learning and SNNs for embedded systems. And this opportunity, I'd like to briefly discuss several books that include methods for energy efficient DNN inference and energy efficient fault tolerant SNN inference under approximate DRAM. Now we are looking into the methods for improving the energy efficiency of DNN inference. In the DNN inference using accelerators, the data is typically partitioned in the form of tiles due to resource limitations. And for each layer of a network, a tile of input feature map and weights are accessed from a DRAM and stored on the on-chip memory at a time. Then these data are computed in the processing elements, producing a tile of output feature maps which is stored in the on-chip memory and DRAM respectively. This process is repeated until all tiles in the layer are processed. However, state-of-the-art works do not consider reducing the redundant access for overlapping data, which should not be refetched again from DRAM. And also, they do not optimize the DRAM energy per access, which may vary depending on the conditions. And the key idea of the DRAM access energy optimizations are minimizing the number of DRAM accesses by reducing the redundant data accesses and minimizing the DRAM energy per accesses. To address these challenges, a Romanet methodology is proposed. Basically, it minimizes the DRAM accesses by managing the data reuse in DNN accelerators. First, it employs an analytical model that considers minimizing the redundant accesses for overlapping data. Then, Romanet determines the data partitioning and scheduling to maximize the data reuse. It is motivated by the fact that DNN model has multiple layers and each having different number of data reuse for different data types. To do this, our Romanet considers the tile-based convolutional loop to explore different combination of data partition and access scheduling to find the one that offers minimum number of DRAM accesses. In the next step, Romanet employs a DRAM data mapping to optimize the DRAM energy per access. The idea is to maximize the row buffer hits and minimize the row buffer conflict and misses while exploiting the multi-bank burst feature and chip-level parallelism. Therefore, for each tile of data, Romanet orderly prioritized to map the data on the DRAM column, bank, row, rank, and channel respectively. Besides data mapping, Romanet also employs on-chip data mapping to efficiently transport the data between the DRAM and the compute engine. The idea is to maximize the data throughput by exploiting bank-level parallelism. Therefore, data from the same tile, which are expected to be accessed subsequently in a short time interval, are placed across banks. The experimental results show that our Romanet reduces the number of DRAM accesses as compared to the state-of-the-art techniques because it considers minimizing the redundant accesses for overlapping data and also more possible scheduling schemes. And here, our Romanet can reduce the DRAM accesses up to 45% for AlexNet, VGG16, MobileNet, and also SqueezeNet. And For the experimental results on the energy saving, we can see here that the Romanet achieves a DRAM energy savings due to the reduction in the number of accesses and also the reduction in the number of row buffer conflicts and misses. And in summary, DRAM access energy saving can be achieved by Romanet up to 46% for LXNet, VGC16, MobileNet, and also SwissNet. Therefore, our Romanet effectively reduces the number of DRAM accesses and also DRAM access energy, thereby improving the energy efficiency of DNN accelerators. Now we are looking into the methods for improving the energy efficiency and resilience of SNNs considering approximate hardware. Employing the hardware level optimization can substantially improve the energy efficiency of SNN inference. For example, through the reduced voltage DRAM or so-called approximate DRAM. However, it comes at the cost of increased bit error rate, and this caused the SNN accuracy to decrease and hence reducing the resilience of SNNs. Therefore, the challenging question is that how to ensure high energy saving considering the approximate DRAM while minimizing the impact of DRAM bit errors on the accuracy of SNN inference. To address these challenges, Spark XD framework is proposed. First, it improves the error tolerance of the given SNN model. The idea is to incorporate the error profile from the approximate DRAM in the training process. This aims at making the SNN to adapt to the presence of DRAM errors. The training process itself is performed by incrementally increasing the bit error rate, and in this manner, the SNN tolerance is gradually improved. Second step is analyzing the error tolerance of the improved SNN. The idea is to find uh, the maximum tolerable bit error rate that meets the target accuracy, which will be used to determine the data mapping in the approximate DRAM. From the illustration, we can see that the baseline with approximate DRAM suffers from accuracy degradation, while the improved SNN maintains the accuracy. And if we consider the minimum target accuracy, then we can see the maximum tolerable bit error rate. This information is then used for DRAM mapping. Afterwards, our Spark XD employs a DRAM mapping to ensure that the train weights are minimally affected by DRAM errors and hence the accuracy is maintained. The idea is to place the weights on the appropriate DRAM partition whose error profile meets the bit error rate requirement. In details, the proposed mapping policy has three main ideas. First, considering the subarray level granularity to enable subarray level parallelism in new DRAM architectures, exploiting multi-bank burst feature to maximize the DRAM throughput, and also maximizing row buffer hits to optimize the DRAM access energy. Following are the experimental results on accuracy. We observed that the improved SNN with approximate DRAM maintains the accuracy within 1% of the baseline SNN with accurate DRAM. We also observed that notable accuracy degradation happens when the bit errors flip the most significant bits of the weights as it changes the weight value significantly. So in conclusion, our Spark XD improves the error tolerance of SNNs as compared to the baseline SNN across different design scenarios. Following are the experimental results for energy savings and throughput. Here we can see that our Spark XD reduced the DRAM access energy as compared to the baseline SNN with accurate DRAM because the reduced supply voltage makes the DRAM operate at the reduced operational power and energy. And the proposed DRAM mapping maximized the row buffer hits and optimized the DRAM energy per access. And here, the reduction of the supply voltage to 1.025 volts using Spark XD saves the DRAM energy by 40% on average. And furthermore, Spark XD also maintains the DRAM throughput because the proposed DRAM mapping maximizes the row buffer hits and exploit the DRAM multi-bank burst features. So, in conclusion, our Spark XD reduced the DRAM access energy while maintaining the DRAM throughput as compared to the baseline SNN with approximate DRAM across different design scenarios. Our publication as part of this PhD work. Following are the co-author publications that use the concept or outcome of this PhD work. This is the end of my presentation. Thank you very much for the attention, and now I will be very happy to answer the questions.